Welcome to lecture 4 of design and analysis of algorithms. Here we will discuss about asymptotic analysis and class of functions. So in the previous lecture, lecture 3, we discussed asymptotic notations such as big O, big omega and theta. So here we will discuss more to asymptotic notation. Those are little o and little omega. So little o here we say that it is strict upper bound. Big O was upper bound. Here it is strict upper bound. What is the meaning? So the change is here. You see here there is no equal sign. In case of big O, so it was what? F of n less or equal than C into Gn for all values of n greater than equal to n naught. It was the definition of big O, right? It was the definition of big O. But here, if I say little o, it is what? Fn is less than C into Gn. Okay, that's why it is called strict upper bound. So we will write using this small letter O. Okay, so in this case, it is less than. So that is the difference only. So here you see the find strict upper bound for Fn equal to 3n square plus 2n plus 3. I have taken the same example. Okay. So what we can write? So we can write 3n square plus 2n plus 3 is less than C into Gn. Now C, let's say I am writing C as 1 and Gn, let's say I am going to choose n cube. Why I have not chosen this value n square, that is the highest order term in Fn, because here you see it must be strictly less. So for the large value of n, we are going to analyze for large value of n. Okay, so for all value of n greater than equal to some n naught. Now let's say that I am writing here 4. So if you put the value of n as 4 here in this inequation, you will see that it will satisfy. Okay, any value greater than equal to 4, it will satisfy this inequation. Okay, now in place of C, what is it? 1. In place of Gn, it is n cube. In place of Fn, the whole thing is Fn, we know. So Fn is less than C into Gn for all value of n greater than equal to n naught. Now n naught, the value of n naught is what? The value of n naught is 4. So we can write what? We can write 3n square plus 2n plus 3 is equal to little o Gn. What is Gn? N cube. Okay. Now the value of C and n naught, this can vary. Okay, we will do that thing by trial and error. Okay. Now the important concept here is that, so here the important concept in case of little o is that if I am saying that Fn is equal to little o, here I will write the term that is greater than Fn. Now in this case, you cannot write that is equal to Fn for large values of n, obviously. Okay. Now let's say I am asking that n is equal to little o n. Is it true? No, it is not true. But in case of big O, it was true, right? In case of big O, n equal to big O of n, it was true, right? But in case of little o, it is not true, because here it should be greater than Fn, right? Now you can write anything that is greater than n, right? Like n to the power 1.5, 1.6. Okay, that will also work. But here only this thing like little o, okay, small letter o. So here I can write n square, I can write n cube, n to the power 4, anything. Yes, those are greater than n for large values of n, right? Now here we can express this little o using this limit. If I say that Fn is equal to little o Gn, then limit n tends to infinity, Fn by Gn is equal to 0 if limit exists. Now you see what is the meaning of it? Meaning of it is that Fn becomes insignificant relative to Gn when n approaches to infinity. Means we are analyzing for large values of n. Now for large values of n, let's say n tends to infinity. Then since Fn is less than Gn, here you can clearly see that Fn is less than C into Gn. So this Fn becomes insignificant relative to Gn. So the value of limit n tends to infinity Fn by Gn will be equal to 0 if limit exists. Okay. Now here in this case, Fn is what? 3n square plus 2n plus 3. So if you find this limit n tends to infinity, Fn, so Fn is 3n square plus 2n plus 3 divided by Gn. Gn is what? N cube. So if you find the value of it, okay, so you will see that it will be 0. Okay, so you can apply L-Hospital's rules and all. So in mathematics, so if you do not know, please revise it, and then you find out this value. So you can apply L-Hospital's rule, and then you will see that it will be, the value will be 0, right? Because here this 3n square plus 2n plus 3, this will be insignificant relative to this n cube for large values of n. So here we are taking n as infinity. So here in summary, if I want to say something about strict upper bound, I can say that always the function fn grows lower than gn. Okay. Now let us see the next one, that is little omega. Now it is strict lower bound, just opposite to strict upper bound. Okay. Here instead of less than sign, here it is greater than. That's it. So here we will write using small omega. Okay. So here if I want to find out the lower bound, let's say 3n square plus 2n plus 3, it should be greater than. So here I will choose the value of c and n naught in such a way that this inequation becomes true. So here let's say for example I am going to choose the value of c as 1 and gn as n. Okay. Now for all value of n greater than equal to 1, this inequation is true. Here you can see that here I have written the term n for gn. Why? Because here the highest order term, excluding the coefficients, here you see it is n square. But Fn here according to the definition greater than C into Gn. Okay. So if this is Fn, so I should select something that is less than n square when the value of n becomes very large. Okay. Now what is C? C here is 1. What is n naught? N naught is also 1. So I can write what? 3n square plus 2n plus 3 is equal to little omega gn. What is gn? Gn is n. Now here the important point. The important point here it is that Fn, if I say, is equal to little omega, here you can write any term that is what? That is always less than Fn. Okay. Now here if I ask you n is equal to little omega of, let's say, n cube. Okay. N cube is equal to little omega of n cube or not? No. Why? Because here you see, here I have written the equal terms, right? So this cannot be equal because it is strictly greater. Fn is strictly greater than c into gn. But if I say that n cube is equal to little omega of n square, will it be correct? Yes, it is correct. If I ask that n cube is equal to little omega, here you see, let's say n to the power 4. No, it is not correct, right? Here you should write such term that is less than, strictly less than Fn. So Fn here it is what? N. So you should write any term that is less than Fn. Then only it will be true. So mathematically, if I write that Fn is equal to, if Fn equal to little omega Gn, then limit n tends to infinity. For large value of n, we are analyzing, that's why n tends to infinity. Fn by Gn is equal to infinity if limit exists. In the earlier case, strict upper bound, this limit n tends to infinity Fn by Gn was equal to 0. But here it is infinity. Why? Because you see here in this case Fn is greater. So Fn becomes arbitrarily large relative to Gn when n approaches to infinity. Now here in this case, if I find out this value, limit n tends to infinity, Fn, what is our Fn? Fn is 3n square plus 2n plus 3 divided by Gn. Gn here it is n, right? So if you apply L-Hospital's rule here, you see it will be infinity because this Fn is what? Fn becomes arbitrarily large relative to Gn when n tends to infinity because we analyze for large values of n. So this is the concept of strict lower bound. So in short, if I want to say something about strict lower bound, I'll say that uh, it is here in this asymptotic notation, strict lower bound, Fn, the function Fn grows faster than Gn. Okay. So these are the concepts of asymptotic notation. So now let us see the properties of asymptotic notation. Okay. So the first property of asymptotic notation, that is reflexivity. All asymptotic notations are reflexive except little o and little omega. Just now we have seen little o and little omega. What is the meaning of reflexivity? Reflexivity means, let's say if I write that Fn is equal to big O of Fn, is it true? Yes, we have seen that here we can write any term that is equal to or greater than Fn. If I write big O, but if I write little o, that will not be correct. Just now we have seen in the previous slide. So that's why except little o and except little omega, all are reflexive. So can I write the same thing for no, sorry, can I write the same thing for big omega? Yes. F of n is equal to big omega of f of n. Yes, because I can write anything here that is less or equal than f in case of big omega. Okay. And in case of uh, theta also I can write. So if I can write these things like Fn equal to big omega of Fn, then it is called reflexive. Okay. So big O is reflexive, big omega is also reflexive, and theta is also reflexive. So because I can write Fn equal to theta Fn, and it is the only correct thing here, right? So except little o and little omega, all asymptotic notations are reflexive. Now symmetry, only theta notation is symmetric. Okay, only theta. Because why? What is symmetry? In symmetric relation, if I want to say that Fn equal to theta Gn, Fn equal to theta Gn, if and only if Gn is also equal to theta f of n. Symmetric means what? A equal to B, then B equal to A. That kind of thing. Here you see Fn equal to theta Gn, if and only if Gn equal to theta Fn. And it is true. That's why only theta notation is symmetric. Why? Because Fn equal to theta Gn. So what you can write? C1 into Gn less or equal than Fn less or equal than C2 into Gn. Now same thing you will write for this notation Gn equal to theta Fn. Then you can see that okay, if Fn equal to theta Gn, okay, Fn equal to theta of Gn if and only if Gn equal to theta of Fn. You can also take an example okay, by taking the uh, expression for Fn and Gn, okay, and this is the symmetry relation. Now, transitivity. All asymptotic notations are transitive. Now, what is the meaning of transitivity? The transitivity is if f of n equal to big O of Gn and Gn is equal to big O of Hn, then we can say that Fn is equal to big O of Hn. It is like A equal to B equal to C, then A equal to C. So that is the meaning of transitivity. You can prove also. Always to prove this kind of thing, always go by definition. Always go by definition. And we have seen all the definitions. Okay, always go by definitions to prove this kind of thing. Okay. So another thing is transpose symmetry. The following notations are transpose symmetry. Fn equal to big O of Gn if and only if Gn equal to big omega of Fn. Fn equal to little O of Gn if and only if Gn equal to little omega Fn. So if you want to prove it, you can prove very important points. Can I write n square equal to big O of n square? Again, I am revising the previous discussion. Yes, I can write n square equal to big O of n square. But can I write n square equal to little O of n square? No, because here I have to write anything that is greater than n square, not equal to. Equal sign is not there. And same thing is for big omega also. Okay, this is true, but this is false. Now, is it true n square equal to little o n to the power 2.135? Like here you see, this is greater than n square for large values of n. So that's why it is true. Here you can see this term n to the power 1.999 is less than n square for large values of n. That's why it is also true. Okay. Now we are going to discuss class of functions. Okay. Asymptotically, this is the relation 1 less or equal than log n. 1 means in constant, right? Less or equal than square root of n, less or equal than n, less or equal than n log n, and so on up to factorial n. Now here you see I have written Tn, means let's say these are the time complexities of any algorithm. Okay. And this is the class they belong to. This is the interpretation, what is the meaning, and then example. Very important table. Now first here you see big of 1. We will say it belongs to constant class. What is the meaning? It is independent on input size n. If input is denoted by n, this is not going to depend on input size. So example, push and pop of a stack. So if you push an item into a stack or pop an item from a stack, that requires what? Constant time, push and pop. Okay. Accessing ith element of an array. So if we want to access ith element of an array, we need to just compute the address of that location. We can directly access. Okay. So that is not dependent on input size. Like if the array size is 10, then it will take, this much time. And if the array size is 1 billion, then it is going to change accordingly. No. Okay. It is independent of the input size. Okay. Now second one here is log n. So it belongs to logarithmic class. Interpretation is what? Each time the input is divided into some portion, usually half. Okay. Each time the input is divided into some portion, usually half. So example, binary search, delete an element from a min heap or a max heap. In binary search, you know that to find uh, an item X, we need log n, because using divide and conquer, if we go with binary search, we'll discuss these things later in algorithm design techniques. Okay? So we can understand from divide and conquer that. Okay, so every time the input is getting divided into some portion, usually half, right? Half of the things are getting cut off every time. So that is logarithm. So linear is simple. It grows at the same rate as input size n. Like linear search, say, or sequential search, same thing. So if I want to find an item from an array using linear search, I need to go through each of the location. So if that array size increases, then the time will increase. Yes, obviously. So that's why it is said that uh, it grows at the same rate as input size n. Now, if you want to add a node at the end of a linked list, so then you need to traverse the whole list to find out that which node is the end node, right? So for that, already you spent what? Already you spent big of n, asymptotically if I say, okay? So these are the examples. N log n, we can say linearithmic or superlinear, okay? Or n log n simply. So here each time the input is divided into some portions, say half, and each portion is solved independently. Very important point. Each portion is solved independently. If there are n portions to solve, then it is n log n, right? Like merge sort, heap sort, quick sort, average case. So this in this operations we need n log n time, right? Then n squared. It belongs to the class squared, right? Squared time complexity, right? So each element is compared with all other elements. Usually two nested loops we use to carry out the operation, like in bubble sort, selection sort, in the worst case of insertion sort. Now exponential, very dangerous time complexity, right? So here all possible subsets of input elements, let's say all possible subsets of input elements we need to generate. Let's say for example, finding power set of a set. So power set of a set, if we know if there are n elements, there will be 2 to the power n elements in the power set of a set. So that time complexity is 2 to the power n. Okay. So this is all for the class of functions. Okay. So next we will see comparing functions. We usually compare different functions in terms of asymptotic order of growth. If we need to compare the functions in order of asymptotic order of growth. When input size n is large, always I am repeating the same thing, like we analyze only when the value of n is large. We don't care about the smaller values of n. So you can do what? You can use the concept of logarithm to compare, eliminate the common terms for better comparison. And the important thing is here is that put very large values of n, because we are analyzing for large values of n to evaluate and then compare. Okay, let's say n greater than equal to 2 to the power 64. It is a huge value, 2 to the power 64, 18 billion or 18 quadrillion, we can say. Okay, now in example 1, here are the two functions given, fn equal to n square log n, gn equal to n log n to the power 10. Now you need to say that among fn and gn, which function is having higher order of growth. Asymptotically, we are analyzing. Okay, so we'll see what we discussed here, the points we discussed, like we can use the concept of logarithm. Now, to go with the concept of logarithm, here I am going to write one important formula for a logarithm, so that we can use that formula. Okay, so that is very useful for solving the problems, this kind of problem. So one is what I can write a to the power logarithm log a to the power log x base b. Then I can interchange this to a and x. Okay, to simplify in some cases. You will see in the example 2. Okay, so here if I interchange, what I will get? X to the power log a base b. This is a very important formula for simplifying the terms. Okay, another thing that is I'll write some logarithmic formulae like log x to the power n n log x. Okay. Now here one thing is concentrate. Here the log that I am writing, this is of base 2. So we can write a shortened notation for that thing. Log n base 2, we can write LGN. Okay. So always I will go with this LGN. That means log n base 2. Okay. So here also you can write those things because we care about base 2 in algorithms. We don't care about those common logarithms or something like that. So if we need to use, then we'll specify. Okay. Next, well, this one is also very important. So here I'll write LG means what? The base is 2. This power k n, this is equal to LG n whole power k. Very important. Okay. Another thing here is that log n is equal to log n. Okay. And the easier things like log xy, you know that you will write log x plus log y, and if it is log x by y, then it is log x minus log y. Okay, these are the logarithmic formulas we need to evaluate. Okay. Now here you see in the first example we need to find out which one is growing faster asymptotically. So if I put the value of n as 2 to the power 64, I told you that put very large values of n to evaluate and then compare. It will be easier, right? So fn will be equal to what? 2 to the power 64, 2 to the power 64 whole square log, this is base 2, LG, log 2 to the power 64. So this is nothing but what? 2 to the power 64 into 2. And then log 2 to the power 64. So here 64 will come this side and then log 2 base 2, that is 1. So 64 multiplied by 2 to the power 64 whole square. So if you do, so you will get 2 to the power 134. So this is the value of Fn. Now Gn. So n we took 2 to the power 64, so 2 to the power 64. So here log 2 to the power 64 whole power 10. So if we simplify that, we will get, here you see 64 will come this side and log 2 to, that will be 1. Then 2 to the power 64 into 64 whole power 10. So if I simplify, this will be 2 to the power 124. Now out of this 2 to the power 124 and 2 to the power 134, which one is growing faster? The growth rate of Fn is more. So here the greater function is, so your answer should be Fn. Fn is the greater. So similarly for this one also, here you see I can do a trick like using this logarithmic formulas. Here you see this formula I can use here. How? So 3 into n to the power square root of n. So this can be expressed as what? This let's say this is 3 n to the power square root of n. Now let's say I will simplify gn. If I simplify gn, so I can write 2 to the power log n, very important, log n to the power square root of n, because here this thing I can send to the power of n. So if I do same using this one, which one? This formula, right? then n log x. So here it will be square root of n log n. So I can send. So what is the point of sending there? Okay. The point is that if I do that, so I can interchange these two things, a and x. So here a and x is what? So here I will write uh, the whole thing, this whole thing, n to the power square root of n. So n to the power square root of n to the power log 2. Okay, this 2 I sent there, and this whole thing came down here. Why? Because here you see the base was here b, here base is hidden, base is 2, right? So we were not going to deal with the base there. Okay, so n to the power square root of n, so we interchange with 2. So these two things are interchanged. So if we do that, then we can simplify. So what is the value? Log 2 is what? Log 2 base 2. It is because LG means what? Log base 2. So log 2 base 2, that is 1. So it is nothing but n to the power square root of n. Now you see it is very simple now. N to the power square root of n, and here it is 3 into n to the power square root of n. So which one is having higher growth rate? Fn. So Fn is your answer. So similarly here also you Fn, growth rate of Fn is less than Gn. If you put the value of n as 64. Okay, so answer in this case it will be Gn, not Fn. Okay. Why? Because Fn equal to n square log n, so it will be n square, right? So 2 to the power 64 whole square n square log n is 2 to the power 64. So you will simplify this and then compare with n to the power 2.5. So the whole thing, this whole thing, if I evaluate, it will be 2 to the power 134. And then if you put the value of n as 2 to the power 64 here, so for Gn it will be what? 2 to the power 64 to the power 2.5. So you will see this Gn, the growth rate of Gn will be greater than Fn. So this is true. Fn is less than Gn. In these two cases, example 1, the growth rate of Fn is more than Gn. In example 2, growth rate of Fn is more than Gn. In example 3, growth rate of Gn is more than Fn. So we have seen how to compare functions. Okay, so in the next lecture, we will discuss about time and space complexity. Thank you.